Engineering, and Dr. Akmal Jahan, Department of Computer Science, Faculty of Applied Sciences, Southeastern University, Sri Lanka. Dr. Akmal Jahan is joining from online. And now I will hand it over to the two chairs. Thank you.
Okay. Good afternoon, everybody. Yeah. So, in the interest of time, I think we better start. I hope other members will join soon. Dr. Kumar, can you hear us?
Yeah, I can hear you.
Okay. Thank you very much. And so, as it was announced, the session 2 of APAN 56 conference, the topic, the theme is accelerated computing and distributed systems. As the first speaker, today we have one presentation on design and development of real-time IoT for multi-cloud factory vehicle monitoring system. The authors are Mr. Pachpong, Mr. Papat, and Mr. Chaudit. And Mr. Papat will, Mr. Pachpong will present. Okay, so it's over to you.
I'm going to talk about the design and development of real-time IoT for multi-cloud factory vehicle monitoring system by me, Pachpong. And I'm from the Department of Electrical Engineering, Chulalongkorn University from Thailand. And my advisor is Associate Professor Chodit, and my co-advisor is Dr. Papat. So let's start from the importance of the factory vehicle monitoring system. So as we can see, the material handling equipment such as forklift is widely used in many industries. So the failure of MHE will interrupt overall production. That's why we need to use IIoT and cloud technologies to support the real-time usage data collection for condition monitoring. So the objective of this project is to design and develop a full stack system prototype to monitor the status of in-factory vehicles by applying IoT and cloud technologies. That means we have three main components. Begin with the physical part, which are the motor drive and microcontroller that we need to design. And the next part is in the clouds that we have the storage system and also the visualize system. And in the application, we will have monitoring website to to monitor the historical record of our vehicles. So here's some key design factors that occur when we design this system. So typically we will use the offline handheld device in order to monitor the status of each vehicle. So that means we have to plug in the handheld to the vehicle to see the status of like battery or motor voltage or current. And then we have to design our own system that act as if the handheld to gather the information and send it to cloud. Therefore, we have to verify the accuracy and the reliability of the data by comparing with the handheld device too. And another key design factor is we use multi-cloud communication. And the last one is we have to design a full stack system to visualize the significant information. This is my system architecture. In the physical part, we will have motor drive, which is inside the vehicles. And we will design the microcontroller to gather those information and send it to the cloud. In the cloud part, we have three main cloud, which is telco cloud, that is corresponding to the microcontroller provider. And the on-premise cloud, we will deploy the front end and the back end server. And in public cloud, we have a database inside. And in application part, we will have monitoring website to see the record of the data and the notification. Here's the software and hardware and software component that I've used to design this system. The motor drive that I use is Curtis 1212S, and the microcontroller is Devio NB DevKit1. The more explanation will be later on. And the telco cloud we will use Magellan, which is the cloud that work together with the Devio. And in backend we use Flask, and front end we use React to develop the system. Those front end and back end will be deployed on the IoT cloud serve at Tian, which is on-premise cloud that we use. And in the database, we will use DynamoDB. Let's start from the first part, which is data acquisition system. So we want to gather the data from the motor drive and send it to the telco cloud. Let me introduce the microcontroller that we use first. This is Devio NB-DevKit1, which is actually ESP32, and it also have NB-IoT connection, which is Narrowband IoT. And the cloud that work with the Devio is Magellan. So the Magellan is cloud IoT platform which can be integrated with the Devio, and they also provide the API and SDK for the developers to develop the system. And they have data forwarding method that can forward data out of the system to other component of our system. And the NB-IoT, which is the module inside the Devio that we have, it's a low power wide area network and use cellular infrastructure to operate the network. And they support large coverage area and consume less power. And they also support massive device connections. That's why we use NB-IoT in order to capture the vehicles, because the vehicle is they can be moving everywhere in the industry or in the factory. And here is here's the processing unit that we design. We have to first one is we have to request data. So this is kind of like reverse engineering, because Curtis they don't have documentation for us that what bytes mean something. So we have to send the request packet according to the handheld device that we have, and then receive those response packet and decode it, that what does that packet mean, and we will validate it if it's valid or not. And after we get the data from the motor drive, we will pack the data with GPS sensor and also temp and humid sensor and send it to Magellan. Here's the installation of IoT device that is my prototype that is being tested right now. And in the database system, after the data is collected in the Magellan, so we have to forward those data to our backend system and put it in the database. So the forward mechanism that we will use push mode, which is actually event triggering. So whenever the data come to the Magellan, it will forward it to our backend and also in the database. The last part is the visualization. So we design backend and front end to record to view the record of each vehicle. The key responsibility of the backend server is the first one is device management. Since the IoT system that we design and the vehicles are separable, so we have to map each IoT device and each vehicle together, so that we can know that which system that we are using with. And the motor drive, we will prepare the records such as latest data or the historical record of each vehicle. And the authentication part, which is we will have role of each user in the monitoring website that will identify the available service that they can use. This is example of monitoring websites. So in the example, we will have like one site that is named Genmanjer, and they have 2 operating vehicles inside and have some recent information in the cards. And if we click in the card, we will have more detailed information of each vehicle, such as temperature, armature current, battery voltage, or motor voltage. So we have to verify the functionality of our system compared to the handheld device. So here is the comparison of monitor data that gained from our system and the actual data that we have from the standard handheld device. So we can see that the trend of the data is the same, but with some lag of time. It is due to the functional of the microcontroller that we designed, because we send it every like 5 seconds, so it have some shift of time over it. So to conclude, our system is try to collect the data from the motor drive, which is inside the in-factory vehicles, and send it to the cloud, which in the cloud we will have storage system and visualize it to the monitoring website. In future work, we can design the optimal period for maintenance by using statistical learning methods or integrate condition monitoring or predictive maintenance with an alerting system. So thank you.
Okay, thank you very much for your presentation. And we'll open the floor for questions. So I have a couple of questions, but before moving to my questions, I think, yeah, go ahead.
I was just wondering whether you're gathering this data from the onboard computer, or is it a different set of sensors, or where?
Yeah, that's fine.
Any specific reason for you to keep the database in the public cloud and the rest of your operations in the on-premise cloud and other clouds?
Hello. Okay, so first of all, the public cloud that we use, because the old system, we have some data that collected inside, so we integrate above them. That's
Okay, thanks.
Yeah.
Thank you. What a wonderful presentation. My one question is that, have you ever thought about the fault tolerance in your system? Yeah, what is the plan? What is the design parameters? If any one of the nodes fails, then how you can cope up with this situation?
Okay, right now it is being in the test phase. So right now I have a prototype of like 7 vehicles that are operating. So we can collect those data and we will further look at it and do some more analytics with those data later. But some simple example is like when the battery level is below 20%, they have to recharge it. If not, if they use until the end of it, the battery will die out, and it will cause the not a good for a battery.
Okay, any more questions? So I have one question now. You install GPS. So within the building, how effective it was?
Right now, the GPS that we install is not it's not always send the information because it used indoor. So some area inside the factory, they have like roof shield. So the data that we have, we don't have all the time, but we will use the latest data that we have.
Uh,
I have one question.
yeah, yes.
How do you validate the data? You may have mentioned that you have validated data. So is there any special mechanism or just?
Yes. Okay. So when we receive, let me show you on the slide. Okay. When we receive the response packet, they will have like 4 or 5 bytes, and then each byte will have their own responsibility. Like the first byte will be the header packet, and there are some redundancy that we have to check whether it is all correct packet or not.
Okay, thank you.
Thank you.
Are there any other questions from the those who are joining online? Okay. So then, thank you very much for your presentation.
you.
Thank you. Let's move on to the second presentation. It's the topic is towards true decentralization, development, testing, and evaluation of a novel blockchain census protocol. Authors are Kesara Vimal and Geeta Priyaliyanage, Mr. Kesara Vimal and Mr. Geeta Priyaliyanage. Presenting author is Mr. Kesara Vimal.
Good afternoon, everyone. Am I audible enough?
Yeah, we can hear you. Please go ahead.
Can you see my screen as well?
This is not the screen, right? Wait for a while. Okay, now it's okay. Sorry. Okay, now it's okay.
Okay.
Yeah, we can start the presentation.
So, my name is Kumudu Kesara Vimal, and here I'm with Mr. Geeta Priyaliyanage, and I'm a postgraduate student from IIT Colombo. Today, I'm excited to present our research paper and demonstrate the software solution that we have created. During our research project, we have focused on addressing a critical issue with current blockchain platforms, which is tendency towards centralization of power. As a solution to this problem, we have proposed a novel consensus protocol called TrueDeck. This is the today's agenda for the presentation, and I will start off with the problem. There are a number of limitations with current blockchain consensus protocols, such as tendency towards centralization, high energy consumption, specialized hardware requirement, discouraging network activities, and entry barriers. The popular proof of work consensus mechanism is what powers the Bitcoin network. And due to the high variance in solo mining, users tend to work together in a mining pool to reduce the variance and get a more chance of mining the next block. So due to this behavior, the Bitcoin mining operation tend to be more centralized, rather it being decentralized as it has initiated. So as you have seen the pie chart which is on the screen, if those two large pools, Foundry USA and Ant pool, comes together, they have the more proportion of the network, more than 51 proportions of the network, which is a risk of 51% attack. Any types of centralization should approach with the caution due to the attack we call in blockchain systems called double spending attack. So which is the tendency towards centralization trends we see in blockchain systems. As an example, I presented the Bitcoin. When it comes to energy consumption, Bitcoin alone consumes more energy than several countries, including Norway. And the carbon dioxide emission of Bitcoin in USA, which is equivalent to a carbon dioxide emission produced by US railway industry. So on the other hand, Bitcoin use specialized hardware resources like application-specific integrated circuit and GPUs in mining operation. Looking at the other side of the coin, the second most popular blockchain consensus protocol, proof of stake, which required users to stake coins in order to participate in the network activities, which also work as an entry barrier. So after carefully examining the literature available on blockchain platforms, the research gap has been identified. Numerous consensus protocol ranging from minor adjustment to Nakamoto consensus protocol to a groundbreaking new consensus protocol has been introduced to the industry in last decade, both from academia and industry experts. However, neither of those protocols has been able to achieve the true decentralization. So the proposed novel consensus protocol offers a solution to this critical problem and which ensure genuine decentralization, safeguarding the core values of blockchain systems. Next, I'm going to discuss about the proposed solution. While addressing the core research question of the project, a novel consensus algorithm to achieve the total decentralization has been designed. The slide discusses the overview of design under each critical point. So complexity plays a vital role in this particular algorithm to keep the block time steady. The complexity is based on two variables, which is the previous block complexity and the time consumed to produce the previous block. The complexity keeps the block time steady, which is around 30 seconds to 90 seconds. And when it comes to leader election, the voting mechanism will be utilized, and soon after each node has been voted and the leader has been elected, the process of block production is starting. So in block production, we have utilized somewhat similar mechanism to proof of work to keep the ledger tamper proof. And finally, the penalty, which plays a vital role also in this particular network by keeping the network secure. So this is not a this is a penalty based system, rather incentive based. So the penalty, if a leader has forged an invalid block, he will be penalized by the network, and his unspent transaction output UTXOs will be added into a separate mempool, and thereafter those UTXOs can't spend by that particular leader elected node. So this mechanism avoid and discourage malicious behaviors and keep this network from going into a double spending attack kind of popular attacks in blockchain systems. I'll quickly go through with the high-level design. So we can see in the design presentation tier contains all the UIs like wallet UI for key management and interface for connecting with peers, and logic tier we see the three main logic: block production, transaction management, and node management. And under the data tier, we see the block chain, mempool, and the routing table. So let's move into the product demonstration. I have utilized Python as a programming language to implement the proposed solution, Flask as a backend framework. Also, I have utilized Python libraries such as Request, PyCryptodome, and Memory Profiler, Snakefish, etc. So I'll quickly play the build solution as a video clip. I hope you can all hear the voice of this.
Mr. Bimal. Mr. Bimal.
Yes.
We can't hear anything. Did you?
You cannot hear the video, volume of the video.
Oh, now I can hear you, but not video is not visible.
It is not clear. The
No, we didn't hear anything from the
be-
go. Is
so,
it over or is it still playing?
from the so, okay. So you can see the video, right?
Yeah, now we can.
The screen, my screen.
Yeah. So it says balance.
So as you can, as you cannot hear the volume of the voice of the video, I will explain quickly of the implemented solution. This is the initial view when a particular node when a node has been powered up. So as this is the initial node of this particular network, it has received 50 coin from the Genesis block as the initial coin offering. Next, we can move into the transaction tab, the second tab, which has the transaction details. And next we have the, it also shows the transaction in a row view. And key management, we see all the keys, wallet address, public key and private key also there. And when it goes to peer management, you can see we can manually add a peer and connect with that particular peer, and we also see all the connected peers. And the blockchain we see all the blocks line by line. So next I'm going to power up another node which is running on a port 3000 to make a transaction and see whether the transaction is happening under the hood. So I'm copying this wallet address of the second node that I powered up and place here, and so 10 coins that particular address. And we can see it has been added to the mempool and wait for the next forge. Now we can see the second node has this 10 added it to its transaction received, and we can see the row view as well with input script and output locking and unlocking script with all those row details. Blockchain also that. Sorry about the issue, the technical issue. I hope you got to understanding of the briefly of the system. So I will quickly conclude the presentation.
Okay, thank you very much.
So I have a couple of slides. Please allow me a couple of 1 minute to complete the presentation. And so when talking about testing and evaluation, so we have done a thorough testing and degree of decentralization. When testing the degree of decentralization, there were no proper metrics or metrics for evaluate such. So we have utilized a framework presented in a paper that has been published in 2020. Under each 5 critical points, we have evaluated that the system we have built have achieved a total decentralization, as system is not depending on any other parties, and each node can submit and validate transaction, and it distribute power among the nodes, and which treat everyone equally and manage not by incentives but through the penalty wise. So when it comes to performance, the CPU profiling and memory profiling, both results are acquired through CPU profiling and memory profiling indicates that it does not require high energy or does not utilize specialized hardware resources. So that conclude it is energy. It does not require specialized hardware. When it comes to energy consumption, the data acquired through open hardware monitor indicates that it only requires 2 to 5 watts, which is typically very much lower with the current available blockchain system, and conclude that the system is very energy efficient. So when it comes to conclusion, novelty, we see this problem has been discussing in the community over the period, but no actual solution has been implemented. But this solution can overcome the issue with this decentralization and can give the true democracy and decentralization to the network. And when it comes to when it discussing the contribution, we have done an extensive literature review by examining various consensus mechanisms and their degree of decentralization, and pinpointed root causes that hinder the true decentralization of many popular protocols, and also we have built this truly decentralized consensus mechanism. So when it comes to limitation in the system, not having a proper coin distribution mechanism and security and scalability can be presented as a limitation. And when it comes to future enhancement, we can also work on these aspects of proper coin distributions, security and scalability can be researched and advanced in this particular system. And thank you for listening to it. I conclude my presentation. Sorry about the technical issue.
Okay, thank you very much. Thank you very much.
Thank you.
Thank you very much. I'll open the floor for questions. Are there questions from the floor? From the online participants, are there questions from your side? There's a question. It's a comment, right? So you may need to select optimize video and audio when screen share. Okay, so in absence of question from the floor, I just wondering now, you mentioned in your initial comment that about the carbon dioxide emission. Now, as I understood, your algorithm is a collaborative one, right?
Sorry, sir, I can properly hear you.
Your algorithm to a certain activity, multiple people join for the same activity to accomplish, right?
Sorry, yeah, can I get the question again? So is it about the carbon dioxide emission?
No. So did you compare with this? I mean, you mentioned, I know that you mentioned it as a comment, but you mentioned about the power consumption as 2 to 5 watt. So
yeah.
Is it, when you to do a certain calculation, you need multiple people, right?
Multiple people, sorry. I think so you are talking about the carbon dioxide emission and the power consumption, as I have got the question. So what I'm going to present is how I have defend my findings, and my how I benchmark my result is I have utilized some of available literature available in the recently published papers, and I have as this is not the network we actually talk about, we talk about the consensus mechanism. So rather comparing with available system like Bitcoin, Ethereum, and Dogecoin or something like that, rather comparing with those particular networks, what I have done is I have been comparing those with a particular consensus mechanism, as the aim of this research and the finding of this research is not the system but the consensus mechanism itself. So I have utilized a set of literature available in this in papers that I have published in recent years, and I have defended my findings and benchmark it against those literature available on the network. So when it comes to carbon dioxide emission, how it is varied from proof of work is the consensus mechanism, this novel consensus mechanism that I have introduced. How it is varied is because how the Bitcoin and the block proof of work, in there every one of the network has to find the nonce, let's say the cryptographic hash. So every node work along to find this particular cryptographic hash in order to get the block reward. But in this case, we are not incentive based but penalty based. Every node in the network has to be do this calculation and work on finding this cryptographic hash. Rather, they have to vote for a leader. So each and every node in the network will vote for a leader, and only the leader will be doing this activity of finding the cryptographic hash for the nodes. So because of that, the only one computer for one block will work on finding this random hash, and the difficulty level is not it's very low compared to the systems like Bitcoin. So that is how I have avoided the carbon dioxide emission and the power consumption when compared with the large network available in industry.
Thank you very much, and I also understand there should be a gain, but then I think as a suggestion, I would rather suggest to substantiate.
I'm sorry, I cannot properly hear you actually.
Hello?
Yes.
I got your point. So thank you very much. And my payment was, if you are going to say that there's a saving in the power consumption, you have to substantiate the point, right? So I think you can improve your research in that side. That's my personal view.
Thank you very much for your feedback.
So since there are no other questions, we'll wind up your presentation. Thank you very much for your presentation.
Thank you very much.
So then we move on to the third presentation. It's enabling of high performance computing and artificial intelligence in space sciences. Author is Mr. Mohammad Ali Ismail. He himself do the presentation. Over to you.
A very good afternoon, everyone. Today, the talk is of title Enablement of the HPC and Artificial Intelligence in the Space Sciences. Before starting my presentation, I would like, this is more going to be a bird eye view, how we can make use of high performance computing and artificial intelligence in the field of data sciences, especially astronomy, without going very in depth or technical details of each of the project, a little bit of projects that actually we are going to. So I will be highlighting that one. So it's just a bird eye view that see how we can integrate the high performance, because actually, obviously from the last 3 days, we are hearing about the importance of the AI and the importance of the HPC. And obviously there are a number of the fields where actually it can be applied, including the financial side, simulation sides, medicine side. Besides, it's also important that they should be much included in the astrophysics, in the astronomical science and the computation sciences. That's important. And that's why I'm just here to present the how we can do it. So starting with the contents, what we actually are going to cover, short of time, and just coming to the big data. Obviously, the big data, and it's a big universe. The most important and the most beauty regarding the universe and the computation sciences or astronomical sciences with respect to the data is that this is the only area, or one of the area where we can find the actual raw data. If we talk about the genomics, if we talk about the DNA, if we talk about the medicine, if we talk about the finance, if we talk about the simulation, it all are the secondary data. It's all data that we have processed with the help of some machines, with the help of some of the equipment. But as far as the astronomical data, the beauty is that it's a pure raw data, where which have a lot of we can do it. We can find a lot of patterns within patterns there. And we can, this is a hidden world where actually we have to look into. So big data is a big universe. And how actually we classify the term big data, now it has been updated with a number of V's, but it started with is a 3 V's. Whenever we talk about the big data, it's a 3 V's: the velocity, the volume, and the variety. If a data is coming with so much volume that you can't store, if the variety of the data is too much that you cannot handle, and is the velocity of a data, it means data is coming so fast, so rapidly that you can't handle with the existing machines, that it can be termed as a big data. And astronomical data is a very good candidate of that one, actual big data. Now, this is obviously that we have to handle the big data first. We have to save it. And obviously with the about the ground speed, space-borne sky surveys, and the gamma rays, X-rays, telescopes we have now, each of the equipments we are just going to place in place, and a huge amount of data avalanches are continuously going to there. So obviously, first we have to save it. First, we have to consider that it's a really a good challenge of big data. Now, another good example, that just a quick glance right now. Look at the Galaxy, SGS, Sky Mapper, GBT, how you can see the amount of the data that actually we have. The most importantly, right now, the SKAs, the square kilometer array, now in which there are number of the radio telescopes are being mapped and being placed in the all around the world. And then it's estimated that 4 exabyte of a data. And means what about we say? We say that most of the supercomputer we have, it contains hundreds of petabyte data, thousands of petabyte data. And 1024 petabytes come into the exabytes. So just it seems how much amount of data we have to handle. So we have to be also, besides all the other professional areas, keeping all the importances in place. But one must have to be seen into that way. And recently, yesterday, that was the example that the Chandrayaan 4 landed on the moon. Actually, this is the world who are going to trace it down, who is going to be a world power. This is all about the space sciences. Starting with the USSR and then the USA and then China and then India and so on, what they are striving for. So keeping intact that space science is also important for us. Don't neglect it. Don't get it. So obviously for that, there's some reasons that we are covered. Now, the first thing that if we have too much data, we really need an infrastructure to handle the big data. And this big data is not going to be considered or going to be handled with as we normally do as using any simple RDMS. We have to develop a new databases. Maybe you have heard about the NoSQL databases. That actually, when we talk about, most of the people who knows about the computer sciences, there's a database, relational database management systems. But only when the Facebook started and LinkedIn started, the data started to grow so much that they have to come up with a new class of a data called NoSQL database. That actually changed the entire domain of that computing database management. And again, now the NoSQL database again is going to be classified into multiple classes. So to handle data, there's a huge amount of framework or the environment we need. We have to first. And obviously, this is the time that the computer science background and the subject domain background should together and start working on it. This cannot be done alone by the subject experts. We really need a group experts members that are involving, and obviously the IT becomes an important part or ingredient part of that one. You can't ignore them. So you go with the Spark, with the Hadoop, Storm, Flink, and any other modes. So to start with, this is the good idea to begin with. Otherwise, if you are continuous doing, so you have a lot of options to do in details. Now, what about coming to the second component, the ML, the machine learning? As I said earlier, obviously there are hidden patterns you cannot identify, and we are trying. Still, the day before yesterday, I was reading that one of the young astronomers from Japan has to find one asteroid, and then one of the celestial object actually, and then going to find a comet, and then comet is being named by his name. So it means there's a lot of every day, even every known young people are just trying to discover the things. So it means there are a lot of hidden patterns here they have to identify. And I was, you will be surprised, maybe I was in a conference and I was talking about that only what we know about the galaxies, about the exoplanets, about the celestial object is the only 3% of the whole universe. And 97% of the universe is still unknown, just called the dark matter and dark energy. It means that are still head-pivot. And the machine learning is the best candidate for it. We always talk about the machine learning to find out the hidden data, to hidden patterns. And obviously we do it. Machine learning is doing it within the financial data, in the business intelligence, in the medicine, and fine. Why not? It should be applied on the machine learning and in the astronomical sciences. So you have a lot of chance when you are getting the raw data, when you are getting the direct data from the sources and just processing it. You have a lot of options there. So these are one of the things. Now, keeping justify my statement that now the people are realizing it, and now you can see from the 2018 and onwards, the yellow stack, you can see the people are started to work on the something integrating the machine learning, and it is a, we can say, is a future. You will find a lot of people doing on this one. And it's going to grow 2018, 19, 20, 21, 22, and 23. You can see the scale of the machine learning related papers in astronomy has started to grow. Besides the theoretical physics, is fine, it's to be had. Now, combining with this is when you talk about the machine learning and big data machine, there can be some challenges associated, obviously. So very specifically, I can say there are the three major challenges that must have to look into. Number one, the big data analytics engine. So I actually say that the storing the data and then applying the machine learning. Now, these are going to be a combined one data, one subset. That's a big data handling and applying the machine learning on that. That's a big data analytics. One have to be expert of that one. Complex calculation. Obviously, when you talk about the simulations, especially in the astronomy and the physics, these are quite NP hard problems. These are not a simple problem. These are not a single equations. These always be a n folded problems and n equatorial problems. So you have to solve it. So for that one, another one of the grand challenge, still is a grand challenge, is that about the n-body simulations. Again, the people are working on that one. If you talk about the 3 bodies and 4 body simulations, okay, fine. But when about you are doing the more than 100 objects of the simulation, and obviously for the 100 objects with respect to the astronomy, with respect to the galaxy, it is nothing. It's nothing. You may talk about 1,000 or 10,000s of the bodies, they are being impacted on each other. So obviously, this is one of the things that's calculation. And in the early keynote, the professor from the NVIDIA was saying same thing, that we talk about, we have to rethink about the calculation. Means we have to go to the basic sciences, and then we have to rethink about, and we have to rewrite the equations, mathematical equations. Otherwise, if we remain stuck on that equations, so obviously, that is not going to be our computation. Current facilities will be failed to attempt that one. It will take a lot of time for that one. And third is the pattern recognition. Again, the advancement of the machine learning algorithms that we can do that, how we find the patterns and that one. I will talk about it later. Now, there are some tools available for the machine learning. If anyone is interested, that he or she can start at its first step. But it's a very basic actually. And what I'm highlighting here is only because they are related to the Python, because we are used to of it. We are C#, C, we are used to of it. So one can easily integrate and start working on that one. For example, AstroML, the Python package for machine learning for astronomy. You can apply the basic classification algorithms there. That might help you that one to begin with initial. And then you can start your classification algorithm to work on deeper and deeper and become the more get a knowledge insight, more insight. Similarly, AstroPy, Skynet, SunPy, Apply, MLA4, Dave, AstroNN, a lot of machine learning algorithms. And you can develop your own as well. Continuously, people are working. Obviously, these are all open source. So obviously, there someone has created that, and you're being available for the others. So now it's a time that you can create that and make it available for the others. Now, computational astrophysics, where I belong to the National Center of Big Data and Cloud Computing in Pakistan, and we have some cloud facility there. And being understanding the importance of this one, we just started the work of computational astrophysics lab, just set up. And what the computational astrophysics lab is doing is all about making that the theoretical physics into a simulation physics, and to current working on that one. So what we have, Raya, where we have a big data analytical engine, the cloud we have. Obviously, there's an important part of that one. So we have some resources of the cloud there to make them happen, to make it especially for the computational astrophysics research, and configured it with the basic principles, libraries and the equations and the frameworks that are available. The students or the researchers can come there. And actually, we are also a part of the Galaxy Zoo. Maybe some of you heard about it. So Galaxy Zoo means there are the international resources fund organizations are also using these resources because for this available. So first of all, the basics is the cloud we have. We are going to start it. Just quickly, some of the projects that we can do, and we have done it, and we have already published it without going very much in detail, is an intelligent celestial objects detection system. When you see on the top and you have a snap of a deep sky, Yeah. Now, how you can identify what object it is and how many object it is? Simply make it. Obviously, when you see on the side, there can be some star, there can be some planet, there can be some exoplanet, there can be some satellite, there can be some asteroid, there can be some anything. There can be a plane as well. So importantly, when you have given a page, if you see, okay, fine, what is this all about? So you can detect the objects. You can count the objects. We have taken a D-Skype image and counted from an algorithm that gives you a 3 million objects on a single way. From a simple image that you cannot find out what it is. So to count that, it's important that you can use the machine learning. Now you are using the big data analytics here and just applying the actual information. And now you can extend the same equation. For example, any of the satellites is giving the image of you. And now you can start that, okay, this is the algorithm. That is a thing that you can work out and find how many objects it is. Further on, intelligent constellation detection system. In the sky, how you can identify the stars, there's actually an axis system. And usually you have to learn about the constellations. So obviously there are about 88 constellations in the whole sky is divided into 88 constellations. So then you get to see the star. Many of the we are heard about only 12 basic constellations, Libra, Cancer, and so on, for which we are actually Gemini, which are but actually there are 88 constellations. Now, when you are given image of deep sky, how you can identify from which part of the sky it belongs? It's also important matter with respect to the solar astronomy. If you first specify which star it is. So whenever your image is given, you can easily identify by the help of the algorithm. Once we have done it in our center, in our lab, that using the simply machine learning and pattern recognition, you can identify which constellations it belongs to. These are one of the very example of that. And if you have done for the whole constellation, unfortunately, from south from our side, in Sri Lanka and Pakistan, we have seen the only northern hemisphere. We can't see the southern hemisphere. That is visible on the Australia side from the other side. So obviously that can be done. If the image is done from here, we can pick it from what actually is all about. Thirdly, extending the project that you have identified the number of objects and you have identified which object it is. It is a star. It may be a galaxy. And now going much deeper into the machine learning, going to much deeper into data, which type of the galaxy it is. It can be a spiral galaxy. It can be a random galaxy. It can be a ring galaxy. It can be a smoke galaxy. It can be a type of the galaxy. Now, start identifying the terms of galaxy. And we have done using the neural network, convolution neural network, the state-of-the-art neural network. Reason that because of a limited number of classification we have. So we applied the best is the convolution neural network. Regular, irregular, spiral, all this. So just an example that we started to find which type of the galaxy. Another very important work that I have recently present in the last 6 months before in the United Nations Forum is the smart sunspot detection system. Surprisingly, I was also surprised too at that time. When I started this project, the sunspot, you see that there is in the sun, there are a number of sunspots there are. Actually, these are because of the explosions there and the fusion process there. Though some of when the dark side, there's a highly burned because the spots there. And there's a great impact on the magnetic force and magnetic radiation that coming to the world. Have a great impact. So the data what we had before that, they usually term in terms of the magnetic parameters is keeping on the Earth and the satellite measured it. Therefore, I started to calculate the sunspots. For the first time, what we have done using the image processing. What we done, we took the 2 last solar cycle data. One solar cycle is equal to 11 years. 11 years. 11 years means 1 year, 365 days. 1 year, 365 means in each year, we took 6 pictures. So just multiply it. It was more than 20 terabytes of our data that we downloaded because of the last life cycles. And we predicted the sunspot for the third coming life cycle that is started in the previous month, in the previous or 2 months before. Now what we have predicted that, we have a graph that one, and now we are matching it to verify that our algorithm has calculated the sunspot, detected the sunspot correctly or not. because the third cycle has started to happen now. And in the last 3 or 4 months, if we got the good answer, so obviously we can easily find that there are some hypes and there that is going to be in the summer or winter. We have some results there. I am not showing there, obviously, whenever I said earlier that because of the time and some issue. So this is a sun spot detection system. And some other more projects are going on. This is a detection system that we have detected original snaps and we have detected it. And then now some more projects that we are doing, N-body simulations that I talked about. Black hole binary simulation is another project which is done by an international organization in joint, that how the black holes, the binary black hole simulation we can do. Again, the use of the AI and ML and the big data, radio astronomy, obviously the number of signals we are receiving here, and obviously if in the terms of radio, and 3D modeling of observable universe is also one of the very, and obviously there's use of the AI and the metaverse. We started our project on the metaverse, means once you have an Oculus and you're in the metaverse environment, you can get into you will feel like you're in a Mars. So we have completed our solar system, but now we are jumping to the others. So obviously this is another project that's under maybe after a 6 month or that would be completed. These things more about can be known about the website sites. So this is from my side. Thank you very much for the patient listening. If you have a question, so please.
Okay, thank you very much for opening a new area for us.
Thank you.
It's a new area for me, particularly. So we can open the floor for questions. Are there any questions from the online participants? Dr. Akmal and other participants?
There's one question.
Yeah,
She did.
Yeah, please.
I'm Shama Wilson from Wovella. Hello, I'm Shama Wilson from Wovella University. So actually, I think I missed the beginning slides. So I'm sorry if I am repeating some questions. So what I want to know, so you are doing the things related with astronomy. So are you maintaining any databases for that can be accessed by students to do projects?
Okay, actually astronomy has a different areas. For example, I talked about the sun that you have heard about. Obviously, there's a different websites, different data sources, and especially from the NASA, ESA. The NASA is a national USA, and ESA is a society from the Europe. So they have a number of these. For example, you are talking about the deep sky images. For that one, you can take any astronomical observatory sites. You can download it. So depending on the area that you work with, so you can find the data source there. And importantly, there's a lot of data freely available here. There's the only domain actually with a lot of data that actually download, you can download, use it.
Okay, thank you very much.
Okay, thank you very much for your presentation. So in the interest of time, we can move on. Right, thank you very much.
Thank you. So nice of you.
Then we move on to our last presentation, Sailing Galaxy, a journey of community growth, deployment architectures, and global services. The author is Mr. Nuwan Gunasekar, Dr. Nuwan Gunasekar, sorry, Dr. Nuwan Gunasekar, and he himself presented. Over to you.
Hi, so I'm going to talk about the Galaxy project. So you might think that I'm here to talk about astronomy, but that's because it's a bit of a misnomer. The Galaxy project is actually a data analysis platform, and it has little to nothing to do with astronomy other than helping with data analysis. So it's a project that has grown in popularity over the past 18 or so years. and can probably be considered a good exemplar of a successful open science project. So I want to talk about Galaxy as some of the key things that help Galaxy to grow, with a view to sharing some of the takeaways we have learned over the years about what helps to grow an open science project. So that may be applicable to your own projects or even your own research. So as I mentioned, it's an open, freely available open source project and data analysis platform with a primary focus on bioinformatics. But in principle, it's domain agnostic. So it can be used for machine learning, which is a topic that was talked about a lot today, climate science, audio analysis. So basically for any domain with complex workflows, backed by high throughput computing, Galaxy is a good choice. So essentially it offers you a web-based UI. You can just sign up and start using it. And you can construct a complex pipeline of data analysis tools, and then you can execute them at scale. So what does it look like? So this is a screenshot of the user interface. So you just sign up and you can start using it. And on the left-hand side, you see a list of data analysis tools. It's not clear, but I just wanted to get the overall idea here. So the list of data analysis tools on the left, and in the center pane, you can graphically construct them into workflows and pipelines and execute and configure those tools to run on your data. And on the right side, it records, as you perform your analysis steps, it records all of the actions you're taking, so you can reproduce them at a later date. So Galaxy can be deployed locally on your local machine, or institutionally, and so on. But there are three main sites that are open and available to the public. The main site is in the US with over 300,000 registered users. Europe has about 80,000 users, and Galaxy Australia is growing very fast with about 30,000 users. And it's across the globe. So with that brief introduction, I'll go into some of the major pillars that have underpinned Galaxy and talk about some of the things that have helped it grow. So if I were to summarize it, it's, accessibility, transparency, and reproducibility have been key pillars that have underpinned Galaxy, and I'll talk about each one in turn. So Galaxy makes your analysis and complex software tools accessible to end users. So for example, let's say you're a tool author, you've written some scientific tool and you want to make it available to somebody else. Even if you make it available to somebody else, they have to figure out how to install it, what software versions to set up. Maybe then you have to figure out how to maybe SSH into a high performance computing system and submit it to cluster, which is fairly complex work and can take up a lot of time. So what Galaxy does is to let tool authors, for example, or somebody who writes a scientific tool, to write a simple XML-based wrapper or a XML description file. And based on that, it can generate a UI for that tool, and you can then combine it and into a complex workflow. So essentially, that's from the tool author's point of view. From the user's point of view, all the user has to do is sign up and start using it, and they can perform the analysis any way they want. So it makes all that work that somebody has done accessible, and planning for accessibility or making your research available to others in some simple, accessible form is a really big growth driver. So to date, there have been over 8,700 tools contributed to Galaxy from people all over the world in a variety of domains. So another thing that Galaxy enables is transparency. So I guess the essence of, in a certain sense, of science is that you can do something and communicate these complex ideas to somebody else in a simple way, so that Galaxy makes that possible because you can visualize very complex data processing pipelines and you can execute them. And of course, you can visualize the results as well within Galaxy. So it makes it possible and easy to communicate your data. So, I mean, essentially, complexity is the enemy, and figuring out a way to communicate your research in a simple way is, again, has been a big driver of growth. Another problem that Galaxy tries to solve quite actively is the reproducibility problem. It's just very strong focus on this. So we've all heard about the reproducibility problem in science, where a lot of scientific findings cannot be reproduced, right? Either the data is missing, methods are missing, the software versions are long gone, or parameters are missing. So it's very difficult for someone else to reproduce your work. So what Galaxy does is that it records every action that you take, the parameters used, the software versions used, and there's a very strong focus on being able to reproduce those results. And not only that, to share it with others. So baking in reproducibility into whatever you do from the very outset really makes a big difference to growth and success of any scientific endeavor. Of course, bringing all of this together is the community that has grown up around Galaxy. So Galaxy recognized from the Galaxy project recognized very early on that there were different types of users, and that all these users had to be brought together somehow, and so that they could collaborate and a good positive feedback loop could be created. So very early on, somewhere around 2010, a community conference was established, and since then it has been happening every year. And that has helped to bring together all of these different types of users and created, it may not be very visible, but it's created about 300 contributors to this open source project, hundreds of deployed instances, and tens of thousands of publications that have used Galaxy. And of course, hand in hand with that is training, because whatever you do, you have to somehow disseminate knowledge about how to do or actually use this software and do something useful. And again, a lot of focus is placed on training that really helped to drive growth and help the community to grow with it. And finally, being able to support a variety of deployment mechanisms, in the sense when you're dealing with, say, for example, protected human data, you have to be able to deal with it in a secure way. So Galaxy has always supported a variety of deployment mechanisms, from HPC systems to Kubernetes, your local machine, for example, you could just run it there. So by supporting a variety of deployment platforms, it has been possible for people to adopt the software more easily and also adapt to institutional constraints. So yeah, that brings me to a close. So the essential takeaways are that I think from Galaxy is that we have to work towards removing as many barriers as possible to communicating your software methods and results. Find a way to communicate complex information in a simple way, that is to say analytical transparency. Add support or build it in from the very outset for reproducibility and sharing. Foster a community and do that early so that your users can grow with you. And of course, needless to say, training is a big factor, and multiple deployment environments. Thank you.
Okay, thank you very much for your presentation and introducing Galaxy to us, and I think it will be very useful for many of us. Right? So are there any questions from your side? Please go ahead.
Yeah, thank you, Niwan, for that presentation. I have actually 3 quick questions. First one is, what are the sequencing technologies that Galaxy focuses on? The next one is, how do you facilitate for the support of these tools that we can deploy through Galaxy? And the third one is, if you can share with us, how does the demography of the users look like? Like if you take country-wise,
Right.
how does it look like? I think that would be interesting to know.
Okay. So, I mean, in terms of sequencing, I mean, short read, long read, nanopore, everything is supported. So it's basically a matter of plugging in because as I mentioned, there are lots of tools that have been submitted, and Galaxy is essentially domain agnostic. So people have done climate science on this and other research areas, artificial intelligence, like deep learning networks. Even those can be run through Galaxy. So essentially, bioinformatics, as I mentioned, is the primary focus. So there are a lot of tools for bioinformatics, and it's fairly up to date in terms of support and for technologies. So I forgot the second question. I didn't hear it. Okay. Right. Okay, I see. So Galaxy doesn't really facilitate it directly other than through training. So you can submit training material and so on to the Galaxy training network. But essentially, all of these servers that I mentioned are publicly available and supported by an administrative team. So if you have any questions, for example, there are people who will answer or help to answer those questions. And they may put you in touch with the tool authors and so on and so forth. So if you're a tool author, I think the best way would be either, making connections with the Galaxy team, as well as contributing documentation and so on to the training network. Yeah. And sorry, there's a third question, I think. So predominantly the users are from the US, but actually a lot of, I forget the exact number. I think it's there somewhere, but I'll have to look it up and get it back to you. But a lot of countries are represented, including Sri Lanka, India, a lot of Asian countries, Japan, and so on. And then European countries, there's a heavy presence, as I mentioned, and Australasia as well. So yeah, so it is growing. But primarily the demographic, a lot of users are from the US. Yeah.
Okay, thank you very much. Any other question on the floor? Are there any question from the online participants? Okay, thank you very much for your presentation. Thank you. So that comes to the end of our session 2. Yeah, for 5 minutes behind the schedule. And to secure the certificates.
Invite Patchapon, Kultum Rongku. Kesara Vimal, Muhammad Ali Ismail, and Nuan Gunasekara. I think he joined us in online. No, sorry, Nuan Gunasekara. Sorry. Okay, ladies and gentlemen, I think we have reached the end of the second session for the conference. And again, I'd like to extend our gratitude to the presenters, the session chairs, and the audience for such an engaging session. And this is the time for us to thank our session chairs. I would like to thank Dr. Akmal Jahan, who joined with us in online mode, and also Dr. Kamalnath Samaragon for sharing valuable insights and raising the occasion as the session chairs. And I'd like to invite Dr. Upul Jayasinghe to present a token of appreciation to Dr. Kamalnath Samaragon. Okay, thank you all very much.